What's going on? My name is Chen Hao, and today I will be talking about the spin-half eigenstates in a magnetic field and their representation on a Bloch sphere. So here's a rough overview, a summary of what we're going to go through today. Um, so first of all, to describe the spin-half particle in a magnetic field, we'll need to write a Hamiltonian down, which is this expression over here. And this will turn out to be a 2 by 2 matrix with complex entries. So it's a 2 by 2 complex matrix. And as with quantum mechanics, the goal is to find eigenstates of the system. And eigenstates are eigenvectors of the Hamiltonian, right? So we will find out that because it's a 2 by 2 matrix, there are two eigenvectors, and they are the plus eigenvector and then minus eigenvector, and we would also call them spin up eigenstates and spin down spin down eigenstates. So I will use the term spin up and plus eigenstates interchangeably. Eigenstates and eigenvectors might be used interchangeably as well, so don't get confused with that. And as well, spin down and minus, I'll use them interchangeably. So when I refer to the minus eigenstate, I'm referring to the spin down eigenstate. I'm just essentially using the same two different words for the same physical object. So we have two eigenstates, and we'll find that, so this will be roughly what the two eigenstates looks like, but we will want to have a more geometrical picture of what these eigenstates represent, and so that will motivate us to express them on the Bloch sphere. So there'll be points. We can express quantum states as points on the Bloch sphere. The Bloch sphere is a two sphere, which is a sphere in 3 dimensions. So it is the one we are all familiar with. Basically, the typical notion of a sphere we have, which looks like something like this. So we'll express these states on a Bloch sphere, and what we'll find out is that these spin up and spin down quantum states, they correspond to antipodal points on the Bloch sphere, which means they're points that are directly opposite one another. So without further ado, I think that's all for the summary we have here. And I might want to add that when we consider the Bloch sphere, the quantum states, the spin up and the spin down eigenstates on the Bloch sphere, it leads to a very nice geometrical picture, which we would elaborate on further later on. So let's get on to it. So first of all, to describe a system, to describe a quantum mechanical system, we need to write down a Hamiltonian, right? So the Hamiltonian in this case is given by H equals to minus mu, where mu is a vector, dot with the magnetic field vector. So mu over here can be written as gamma times the spin of the particle. It's not important to know what gamma is over here. We'll see that they're just constants that does not concern us in this video. So this can be written as S dot B, and we can further simplify it. We can further write it as in terms of the Pauli vector. This is known as the Pauli vector, and this would lead to an expression like this, and the dot product is commutative, so I'll just write it in this form to make it easier. So this Hamiltonian over here is our object of interest, and what we want to do is we want to find eigenvectors of this Hamiltonian. So let's examine the terms. The first term we have here is just a scaling. We just scale the eigenenergies, the eigenvalues up by this factor. So it's not of great importance to us, but what is of interest to us is this term over here. Let's see what this means. So for the magnetic field, it's just the magnetic field we're all familiar with. It's a vector in 3 dimensions. There's x, y, and z component, and it will be useful to write this as b naught, which is the magnitude of the vector, times n hat, which is the direction of the vector. And we'll see soon that it is very convenient to express the magnetic field in terms of polar coordinates. So what are polar coordinates is basically expressing a magnetic field vector b in terms of the angles it makes with the axes. So let's see if I can draw this correctly. y, so it'll be something like this. This will be angle theta, and then project the magnetic field down and find the angle it makes with phi. So this can be written as, so b arrow, the vector can be written as the magnitude times sine of sine of theta, cosine of phi, sine of theta, sine of phi, and cosine of theta. So this is basically the unit vector, the n hat unit vector in a certain direction where the direction is labeled by angles theta and phi. So if I'm sure we're familiar with this, and yeah, so this is what the B vector is, and what is this poly vector over here? Well, the poly vector similarly has x, y, and z components, but it's not exactly a vector with real components or complex components. And to be more specific, this is a poly matrix over here. It's the X is the first poly matrix, second poly matrix, and third poly matrix. So sigma of X is actually a matrix in itself. I minus I. And yeah, so what this means over here is that when we have B, we have B dotted with the poly vector, what that actually gives us is bx sigma x plus by sigma y plus bz sigma z. And this in turn is bx times the entire poly matrix. So it'll be 0, 1, 1, 0 plus by 0 minus I 0 plus bz 1 minus 1, 0, 0. Yep. So this, if we write it out, it will be bz bx minus I by. You can check it for yourself. Bx plus I by and minus bz. So this b dot poly vector, this on first sight we might expect it to be a scalar because it kind of looks like a scalar. A dot product kind of looks like a scalar, but in fact this is not true because the poly vector is not a vector with components of real numbers or complex numbers. It's each component, the xyz components of the poly vector is actually the poly matrices. So this is in fact a 2 by 2 complex matrix. And just to show you that I am not really making this up, this is the Wikipedia page on poly matrices. You can see this is the poly matrices over here, and over here they have a section on the poly vector. So the poly vector is defined to be this quantity over here, and when you have a vector dotted with it, it corresponds to this matrix. And this matrix looks exactly like the matrix we have there, except for A, we have B. So yeah, so I hope that explains our Hamiltonian well. And yeah, so in order to find the eigenstates, we know that the we know that the Hamiltonian is a 2 by 2 complex matrix. So we want to find the let's ask if we can find the eigenvectors of the Hamiltonian. We're going to find the eigenvectors and eigenvalues. Sorry, the eigenvalues will not be of great importance to us in this video, but we can briefly state it. So we want to find the eigenvectors in order to solve the system, solve for the system. So as it turns out, let's check out the Wikipedia page again. Wikipedia provides a very nice exact solution for the eigenvectors. It says that given this matrix, its unnormalized eigenvectors are these. So because it's a 2 by 2 matrix, there are 2 eigenvectors with their corresponding eigenvalues, and the eigenvectors are given to be this expression over here. So if we just substitute that in, so let's see if we go over here. Yep. So we have b dot poly vector, b magnetic field dot Pauli vector, and we're going to find the eigenstates. So there are two eigenstates. There's a plus, and there are two eigenstates, and we just call them plus and minus for now. So it equals to some eigenvalue. Let's call it lambda plus and lambda minus. So the expression for the plus eigenvector, the spin-up eigenvector, is given by bz plus magnitude of b bx plus iby. You can check that this is consistent with the form given here. And for the minus eigenvector, for the spin down, we have minus bx plus iby bz plus magnitude of the b vector. So may I just remind you that we have written b dot sigma as this matrix over here with these entries. This is the matrix we're looking at right now. And just now we have found a more convenient expression, not convenient, we have just found another expression. Okay, I guess we can call it convenient. We have found an expression for b vector to be this. So sin theta cosine phi, sin theta sine phi, cosine theta. So what we can extract from this information is that the bx is then b naught sine theta cosine phi, by is then b naught sine theta sine phi, and bz is then b naught cosine theta. So if you just substitute in the values of bx, by, and bz, I mean the expressions of bx, by, and bz we have over here into our spin up and spin down eigenstates, we can find that the spin up eigenstates can be expressed in terms of theta and phi. So okay, over here it's not really exactly correct to write that is an equal sign over here. It's more appropriate to write it as proportional to, because these eigenvectors stated in the Wikipedia page, they are not normalized. So what normalization is basically the condition that when it's dotted with itself, it must be equal to 1. And similarly for the minus eigenvector. So you can see later on, so that's why I write a proportional sign here. Later on, we will scale it by a certain factor in front, and in order to ensure that the plus and the minus eigenstates are normalized. So currently, these are unnormalized. These are unnormalized. And this is the normalization condition. Yep. So let me just draw a small box over here. Yeah. So let's first substitute in the values of bx, by, and bz over here into our first spin up vector. So bz will be b naught cosine theta, as you can see over here, plus the magnitude of the b vector is just b naught. Then bx is b naught sine theta cosine phi, and iby is then I b naught sine theta sine phi, and this is equals to b naught. You can pull out the factor of b naught, cosine theta plus 1, and at the bottom here we have sine theta, it's a common factor, and then cosine phi plus I sine phi is just e to the power of I phi. Yep. And we can further express this in half angle formula or double angle formula, however you want to see it, and get that. Let me just find a space to do this. At the corner over here, cosine theta equals to 2 cosine squared theta over 2 minus 1, and sine theta equals to 2 sine theta over 2 cosine theta over 2. Am I right? So these are the trigonometric identities that we're going to apply. So we can get over here is 2 cosine squared theta over 2, and at the bottom we have e to the power of I phi. Let's write that first, and then 2 sine theta over 2 cosine theta over 2. Now we can pull out the factor of cosine theta over 2 to get b naught cosine theta over 2, and so at the top we have we have 2b naught. So at the top, so we pull out the factor of 2 cosine theta over 2, and at the top we have cosine theta over 2 left over, and at the bottom we have e to the power I phi sine theta over 2. Now remember we said that the spin up eigenvector is proportional. Is proportional to this term over here at the very first, but we said that because it's unnormalized, it's not exactly equal, because in order the spin up eigenvector has the condition, it has to satisfy the normalization condition. So the spin up eigenvector is proportional to this vector over here. It's not exactly equal. So we can get that the spin up eigenvector is proportional to this vector over here. So if we apply the normalization condition, we can see very neatly that this term has the length of 1. So that allows us to write the spin up eigenvector as cosine theta over 2 e to the power I phi sine theta over 2. And this of course satisfies the normalization condition. So you see the scaling of the vector we did over here. Well, because that is due to the fact that we can have a certain vector, a certain eigenvector, right? And we can scale the eigenvector up by an arbitrary number, let's say c. We can scale the eigenvector up and it will still remain an eigenvector. In other words, the scaling does not cause the eigenvector to lose its eigenproperty. So because we can scale any eigenvector by a constant and still get an eigenvector, we can scale the unnormalized eigenvector by any constant and still get an eigenvector. So in essence, that is what's going on here when we say there's proportional to. So in the end, we have a nice expression for the spin up eigenvector. So this is the spin up eigenstate. Eigenstate and eigenvectors are used interchangeably. So we can repeat a similar process for the spin down. So the spin down is equals to, if you wish, you can just skip the mathematical steps and I'll go a bit faster here. I'll do a bit less explaining. So it'll be this minus sine theta cosine phi plus I sine theta sine phi, and at the bottom we have cosine theta plus 1. This will then pull out to be b naught minus e to the power of minus I phi sine theta, and at the bottom we have 2 cosine squared theta over 2. Then we can pull out this factor over here, so minus e to the power of minus, sorry, let's do the sine, the half angle first. We pull out the factor of 2 cosine theta over 2, and we can get, this is minus e to the power of minus I phi sine theta over 2 and this will be cosine theta over 2. And in turn, we can get that the minus eigenstate is proportional to, if we pull out the minus e to the power of minus I phi, we get theta over 2 minus e to the power of minus I phi, and at the top we just get sine theta over 2, and at the bottom we get minus e to the power of I phi. You can check that this multiplied by this would cancel out. The minus and minus will cancel, and they are conjugates, and they are just a phase factor. So yeah, so in the end, if we apply the normalization condition on the minus eigenstate, the spin down eigenstate, if we apply this, if we impose this condition, then we can get that this is the expression for the spin down eigenstate. So yeah, let me just highlight that over here. Sorry, the highlighting is a bit off. And this will be our spin down eigenstate. Now it is important to emphasize here that although these eigenstates, they are sort of invariant under a phase factor. So remember, we imposed the normalization condition, and yeah, so there's a condition that sort of, so at first we can say that if we don't have this condition, let's say we do not impose this, in the hypothetical situation that let's say we do not impose this condition, then the plus eigenstate can be any constant, right, in front of it, and we can multiply it by any constant and it will still remain a physical quantum state. But once we impose the condition, let's say we impose this condition, then it means that we cannot multiply by any constant in front now. Now we must multiply it by a constant c, where magnitude of c equals to 1, and that as a complex number is just a phase factor. So what I'm trying to say over here is that even though we have imposed the normalization condition, and if plus is an eigenstate, remember it's an eigenstate of h, then e to the power of I alpha, where alpha is any real number, if we multiply by a phase factor, is also an eigenstate of h. And this is, in a sense, why they say that quantum mechanics is invariant under a global phase factor. Okay, in this case, we only have one state, so the idea of global is not necessary, but this is why they say that the quantum mechanics, it is blind to the phase factor. So the phase factor does not affect the quantum mechanics of our system. So yeah, so what we have over here is that the plus and minus eigenstates, you can multiply them by any phase factor, and in a sense we chose the phase factor to be a factor that makes the first component of the eigenstate real, and you'll see why that is important later, because when we want to express it on a Bloch sphere, we needed to massage it into a form that looks something like that. So this is yeah, so I will now take some time to elaborate a bit of why we call it spin up and spin down. So let's see what we have here. So I'll go to a new page here, and we have a, so let me let's see how I want to do this. I want to talk about why can we call plus the spin up eigenstate, and why we can call minus the spin down eigenstate. Why can we call it that way? It's not just any random name that we made up. There's a motivation behind the name. So to explore the notion of spin up and spin down, we need to introduce the spin operator. So as we talked about previously, we have the spin operator. You might have seen just in the previous area. Let's see. Previously, we defined the spin operator to be over here. This is the spin operator. And if we apply that spin operator, so as in quantum mechanics, if you want to take, so in quantum mechanics you have quantum states, right? You have quantum states psi, and then if you want to extract information from this quantum state, you need to apply an operator on it. Let's say I want to extract the spin on it, so I'll apply this spin operator on the eigenstate, and I want to find its eigenvalues. And the eigenvalues corresponds to the measurements that we'll get from the experiment. So we have the notion of spin operator. So what is a spin operator? The spin operator in the n hat direction is in a certain direction is given by h bar over 2 n hat dot Pauli vector. So what is this n hat over here? So this n hat over here is a direction we define it to be. So what this means is that when we talk about spin up, this is a very important point I want to illustrate. When we talk about spin up, we're not talking, we usually, when we talk about spin up, we need to specify the direction it is spin up in. So it does not make sense to just say spin up. It does not make sense to just say this particle is spin up. It only makes sense to say it is spin up in a certain direction. So for example, spin up in the x hat direction, or perhaps you want to say spin up in the y hat direction, or spin up in the z hat direction, or for an arbitrary direction, spin up in the n hat direction. So yeah, similarly for spin down, it only makes sense to say spin down in a certain direction, and it does not, in a sense, there's no universal direction to follow. When you say that a particle is spin up, you must always say it is spin up in a certain direction, and in this direction we call it to be let's call the direction n hat. So back to the spin operator, when we want to extract the spin from a quantum system, we have the operator over here. This operator will be applied to the quantum state, and there'll be eigenvectors of this operator. So if we take this as the definition, this is the definition for the spin operator. Okay. So what we can check over here is that if we let n hat be the direction of the magnetic field, remember previously we said that b arrow equals to b naught times n hat. If we take this n hat to be the direction we want to measure the spin in, so we take this as the direction, we take n hat as the direction to measure the spin. Then remember that the eigenvectors of the b dot sigma were the plus eigenstate and the minus eigenstate. So this vector over here will actually be b naught yeah. So what I want to say over here is that what I want to justify over here is that when we call the plus eigenstate the spin up eigenstate, what we're actually trying to say is that when we measure the spin of the plus eigenstate, we get a value of we get a measurement value of plus h bar over 2. And this is why we call it the spin up eigenstate. And similarly, if we measure the direction of the minus eigenstate, we get an eigenvalue of minus h bar over 2. So in essence, this is why we call the plus eigenstate and the minus eigenstate to be spin up and spin down eigenstates respectively. So this naming convention did not just come out of nowhere, because it sort of corresponds to physically spin up and spin down eigenstates. These are the values you get out of the measurement by the spin operator. So yeah. So if I want to take this time to give a quick shout out to this video over here on before we move on to the Bloch sphere. I just want to elaborate that I just want to refer you to this video over here that talks about spin in a very concise manner as well. Specifically, you see, this channel is Noah Explains Physics. Shout out to him if you're watching this. Hello. Yeah. So where I paused at in this video is that he just showed that n hat dot the Pauli vector applied on the spin up eigenstate. You can see the spin up eigenstate is the exact one we have in our own drawing, in our own equations. When we apply the n hat dot Pauli vector on the spin up eigenstate, he does in fact get a eigenvalue of +1, and this is exactly what he has. So I will not go through the mathematical details of this equations over here. What I'm just trying to say, I just want to illustrate the point of why we call it the spin up and spin down eigenstates. And Noah's video does a great job of explaining and going through the mathematical details of why this is true. So yeah, so if you want to find out why this is true, refer to Noah's video. Yeah, once again, his channel is great, his video lecture is great, so check him out. So yeah, so now that we have the spin up and spin down eigenstates, and let's just do a quick recap of where we have gone through so far, what we have gone through so far. So we started off from exploring. Let's change the color of the pen I have over here. We started off by exploring what the Hamiltonian describing the system is, and then we found out that the Hamiltonian contains this term, this b dot Pauli vector term, and then we unpacked what the b dot Pauli vector is, what that term is, and we got this expression over here. So then we wanted to find the eigenvectors of this matrix over here. We want to find the eigenvectors, and what we have found is that we have a very nice expression for the anomalized eigenvectors. Which are spin up and because there are two eigenvectors, we called them the spin up and spin down eigenvectors. And then we see that the spin up and spin down eigenvectors depend on the quantities bx, by, and bz, and then we express bx, by, and bz in terms of polar coordinates. So bx, by, and bz are now functions. Bx, by, and bz are now like they're expressions in terms of the angles theta and phi. So now bx, by, and bz, we express it in terms of polar coordinates, which gives us an expression in terms of theta and phi. So if substituting in the values of bx, by, and bz into our eigenstates, we can find that we can express our spin up and spin down eigenstates in terms of theta and phi as well. And we have to do expressions of the spin up and spin down eigenstates in terms of theta and phi. So it is important to remind us where the theta and phi came from. So where the theta and phi came from, if we refer up to the definition of theta and phi here, this is where it came from. This is where it came from. Let me just draw a star. It's kind of ugly. This is where the theta and phi came from. It came from our definition when we expressed the magnetic field in terms of polar coordinates. So theta and phi, sorry for that, theta and phi is, where did it come from? The answer is, it came from our definition of the magnetic field vector when we expressed it in terms of polar coordinates. Yep. So our theta and phi came from the polar coordinates when we expressed the magnetic field. And now we have the spin up and spin down eigenstates in terms of the same theta and phi. So yeah. So then we took a short detour and we talked about why we can call this spin up and spin down eigenstates. It's because when we have a spin operator in the n hat direction given by this expression here, we can check that the spin up and spin down eigenstates are in fact eigenstates of the spin operator with the eigenvalues of plus h bar over 2 and minus h bar over 2. And this justifies the naming of our plus and minus eigenstates to be spin up and spin down eigenstates respectively. So I would like to once again reiterate this point over here, that when we talk about spin up, it's always in a certain direction. It does not make sense to say it is universally spin up, because spin up or spin down always depends on a certain direction. So what might be, let's say we have a vector over here that is spin up. Sorry, what am I saying? Let's say we have a state over here which is spin up in a certain direction. Let's say that direction is x. Let's say we have a quantum state phi, which is spin up in the x direction. It might be spin up in the x direction, but it is not going to be spin up in another direction, y hat, let's say. So the notion of spin up and spin down really strongly depends on the direction we're talking about. And in this case, sorry, let's use another color. In this case, when we're talking about spin up and spin down eigenstates, they are spin up and spin down in the n hat direction, where n hat is defined when we define where n hat is in the direction of the magnetic field. Yeah, so it's in the n hat direction, and n hat is the direction of the magnetic field. So these are spin up and spin down in the plus and minus eigenstates are spin up and spin down eigenstates in the n hat direction, where n hat is defined to be the direction of the magnetic field. So I hope that clarifies any confusion we have. This was certainly a confusing point. Confusing point that I struggled through, and yeah. So now now they have covered now they have covered the two eigenstates of the Hamiltonian, the system we're describing. Let's see whether we can have a more neater picture for the eigenstates. So let's find some new space over here. So yeah, so now once again we have the plus eigenstate, which I'll just put it up here for later reference, and we have the minus eigenstate, which I'll put it up here as well. So these are the two eigenstates. These are the two eigenstates we have for our system, our quantum mechanical system. And the two eigenstates correspond, the two eigenstates are the spin up or spin down eigenstates. And why we called it so is because when we apply the spin operator in the n hat direction on them, we do get the spin, we do get a spin up and spin down eigenvalues out of them. So let's express this on something known as the Bloch sphere. So what is the Bloch sphere? Let's head over to the Wikipedia article over here. The Bloch sphere is a way to express a quantum state as a point on the three-dimensional sphere. So let me say that again. The Bloch sphere is a way to express a quantum state that we have as a point on the sphere. So Noah's video explains this very well actually. Let me jump to the point when he talked about it. Yeah, he talked about how we can convert the quantum state that we have into something known. The quantum state we have currently is a two-dimensional vector, right? And it has complex entries. Well, we can convert that two-dimensional vector into a three-dimensional vector that is a point on a sphere known as the Bloch vector. So this gives us a better geometrical picture of what the quantum state represents. And if we take a look over here, you can see that the Bloch sphere once again is a geometrical representation of a pure state space of a two-level quantum system. Don't worry if the terms here don't make sense. It just means that we can express our two-dimensional vector as a point on the Bloch sphere. And yeah, I hope that makes sense. And so so what exactly is this conversion? So how can we convert a quantum state, which is a two-dimensional vector with complex entries C1 and C2? How do we convert it into a point on the sphere, which is a three-dimensional vector? So it turns out this conversion is simply Noah does a great video about this. Once again, if you have time, please check him out. And if you don't understand my explanation, his explanation on the Bloch sphere does it does help you understand it in more detail. So to convert it, to turn the state vector that we have into a point on the sphere, we apply this transformation on it. So we have the bra over here, the poly X matrix, and the ket. So this is how you map a quantum state onto a point on Bloch sphere. So and it is possible to go the other way around as well. So Noah also goes through the mathematical steps of this in very great detail. He says that a Bloch, you can see over here, a Bloch vector corresponds to a quantum state of this form. So if we express the Bloch vector in spherical coordinates, if we express the Bloch vector in spherical coordinates, then we can obtain a quantum state, and n hat over here in the subscript just denotes that it comes from this Bloch vector n hat, as we can express we can find that the Bloch vector maps to a quantum state that is of this form. And yeah, we can take a look at we can double check this with the Wikipedia article as well. You can see that the definition of a Bloch vector is that there's a way to write, if we write the quantum state in this expression over here in terms of cosine theta over 2 and e to the power I phi sine theta over 2, then with the parameters theta and phi can be reinterpreted as spherical coordinates as a point on the Bloch sphere given by this Bloch vector over here. So yeah, so with this idea of the Bloch sphere in mind, I did not add a title. This idea of a Bloch sphere. This is the idea of a Bloch sphere. Well, with this idea, let's see where our two quantum states, spin up quantum state and spin down quantum state, spin up and spin down eigenstate. Let's see where it maps to on the Bloch sphere. And what we'll see as a spoiler is that they actually corresponds to antipodal points on the Bloch sphere. Antipodal meaning opposite points on the sphere. So yeah, so later on we'll see that when the spin up eigenstate is mapped onto the Bloch sphere and the spin down eigenstate is mapped onto the Bloch sphere, they are in fact the 2 points on the Bloch sphere are in fact antipodal. So yeah, so without further ado, let's try to express these spin up and spin down eigenstates as points on the Bloch sphere. So let me just try to draw a huge Bloch sphere over here. So we have exists in 3 dimensions. So with the x, y, and z component, x, y, and z directions. So yeah, we have the x hat, y, z hat, and the y hat directions, and we want to find where our quantum state, the spin up quantum state, corresponds to. So I'll denote the spin up quantum state in green over here. So once again, we have the expression and we can see that this expression is very nice because it is of the form cosine theta over 2 plus I phi sine theta over 2, meaning that this directly corresponds to a point on the Bloch sphere. So the point on the Bloch sphere is denoted, the point on the Bloch sphere corresponding to the plus eigenstate is denoted by n hat plus, to mean that it comes from the plus eigenstate, and this is sine theta cosine phi sine theta sine phi and cosine theta. So if we draw this as a point on the Bloch sphere, let's use green. So it corresponds to something like so this is the vector n hat plus, and it corresponds to the eigenstate plus the spin up eigenstate, the plus eigenstate. And if we find where this point on the Bloch sphere is given by this expression, it corresponds to a point where the angles here is theta and the angles is theta and phi, basically spherical coordinates. Basically this translates to a point on the Bloch sphere that is labeled by angles theta and phi. And so this is what we have for the spin up state. And it is now the right time to illustrate why this picture is it helps us in our understanding. It's because let's remember where the parameters theta and phi came from. The parameters theta and phi they came from our definition when we expressed b arrow in terms of b naught times n hat, and the parameters theta and phi, they came from our expression of the magnetic field vector in polar coordinates. You see, the angles theta and phi, they did not just come out from nowhere. They came from our expression of the magnetic field in polar coordinates. So from here, when we have gotten from this system, we have gotten that the spin up eigenstate is of this form, and when we represent the spin up eigenstate as a point of the Bloch sphere, it corresponds to the same angle theta and phi. So this sort of means that if we overlay the pictures of the magnetic field and the representation of the spin-up eigenstate as a point of the Bloch sphere, the spin-up eigenstate is in a sense aligned with the magnetic field. So let me just draw it over here. This is the incredible geometrical picture that the Bloch sphere offers us. So it is as if if we put the magnetic field vector as a arrow, as a vector on the same space as the Bloch sphere, the spin-up eigenstate is aligned with the magnetic field vector because they are parameterized by the same angles theta and phi. So yeah, so this is the geometrical picture that the Bloch sphere offers us, that this representation of the quantum state cannot offer us. So once again, let me just reiterate why. I hope this explains why it is beneficial to express the spin-up quantum state as a point on the Bloch sphere. It is because it gives us the geometrical picture that the spin-up eigenstate is aligned with the magnetic field because the spin-up eigenstate is parameterized by the angles theta and phi, and the magnetic field is also parameterized by the same angles theta and phi. So this, you can see that if we just stopped over here for the expression for the spin-up eigenstate, we would not have gotten that elegant geometrical picture out of it. But because we went to convert it as to a point on the Bloch sphere, we now have this very intuitive picture of what the spin-up state represents. The spin-up state is aligned with the magnetic field. And similarly, so I hope that this blows your mind and makes expressing the spin-up eigenstates as a point of Bloch sphere rewarding in a sense. And that prompts us to ask another question, which is if the plus eigenstate corresponds to a point of the Bloch sphere that sort of aligns with the magnetic field, is in the same direction as the magnetic field, then what does the minus eigenstate give us? What does the minus eigenstate map to? So to do so, we just need to find where, let's proceed with the mathematical steps to express the minus eigenstate, the spin down eigenstate, as a point on the Bloch sphere. So I'll write it over here because there's more space here. So the spin down eigenstate, once again we have this expression. With this expression over here, and if we want to express this as a point on the Bloch sphere, what we need to do is we need to recast it into a form of cosine some angle over 2 and e to the power of I some angle sine some angle over 2. So what I'm trying to say over here is that when we converted the spin up eigenstate into a point on the Bloch sphere, it was very easy because the conversion was already essentially there for us. Because in order to convert a state into a point on the Bloch sphere, we first need to express it in such a form. We first need to express it in such a neat form where cosine some angle over 2 and then e out I some angle and sine some angle over 2. We need to express it in this form, and then it corresponds to a point on the Bloch sphere given by the parameters theta and phi. So it essentially to express on a Bloch sphere, if we want to go from a quantum state to a point on the Bloch sphere, we first need to write the state as cosine some angle I'll call alpha over 2, and then e of I some angle we'll call beta sine alpha over 2. And then we can get that the corresponding, perhaps I should have explained this when we first talked about the Bloch sphere, but now that we are onto the minus eigenstate example, it's less easy, so that's why I'm re-explaining it again. So as I was saying, we first write the eigenstate, we first write the quantum state in this form, and then the corresponding point on the Bloch sphere will be given by sine theta cosine phi, sine theta sine phi, cosine theta. So these are the steps to express it on the Bloch sphere. So once again for the plus eigenstate, it was extremely easy because the angles were essentially there for us already, right? The angles are just simply theta and phi. You can just read off the expression that we had. But for this minus eigenstate, it is less easy because you see over here we have a sine, and here we have a cosine, and here we have a minus, which is not the right terms. So we need to re-express it as cosine of some angle alpha over 2 e to the power of I some angle beta and sine some angle alpha over 2. And so let's ask the question, what is alpha and beta that can satisfy this expression over here? So we want to find alpha and beta such that this expression, this equality, holds true. And it turns out it's almost obvious over here that alpha is equals to pi minus theta, and beta equals to pi plus phi. So if you substitute these values into this expression here, you immediately get this result. So once again, I will not go through the mathematical steps over here, but Noah actually does a great video on it. Let me see if so Noah actually does a great video on this. Let's wait for it to load. At around the timestamp of 30 minutes, he does explain this in great detail. As you can see the outline. He says that phi goes to phi plus pi and theta goes to pi minus theta. So yeah, I will not go through this in mathematical detail, but Noah definitely does it. You should be able to work it through yourself. And so now that we have expressed the minus eigenstate in this form, this means that the minus eigenstate as a point on the Bloch sphere, it maps to n hat minus equals to sine alpha cosine beta sine alpha sine beta and cosine alpha. Am I right? Then if we substitute these values in, what we can eventually get is that this is minus of sine theta cosine phi sine theta sine phi cosine theta, and this is minus of what we had for our plus eigenstate. So over here, let me reiterate what I just did. So first, we looked at the plus eigenstate, the spin-up eigenstate, and we said that the spin-up eigenstate was a point on the Bloch sphere corresponding to these values here, corresponding to this expression over here. The n plus hat is this value, and this is in a sense aligned with the magnetic field. Well, what we have now over here is that the quantum state, the quantum eigenstate minus the spin down eigenstate corresponds to the point on the Bloch sphere that is negative of what we have for the plus eigenstate. So the plus eigenstate, this is the n hat for the plus. So what we have is that it is negative of the vector, so that's just an inversion. So this is n minus hat. So if we look at the Bloch sphere, that just corresponds to antipodal points, am I right? So if we express the minus eigenstate, the spin down eigenstate, as a point on the Bloch sphere, what we can get is that corresponds to a point roughly like this. So this is the minus eigenstate, and the vector that the Bloch vector that it corresponds to is in fact minus of n plus. So what I've said before, and what I will say many times again, is that the two eigenstates we have, the plus eigenstate and the minus eigenstate, the spin up eigenstate, and the spin down eigenstate, when we map these 2 points, the points on the Bloch sphere, we get that they are antipodal points, meaning one corresponds to the vector, to the Bloch vector, and the other corresponds, one corresponds to the plus eigenstate, corresponds to a Bloch vector that aligns with the magnetic field, and the Bloch vector that corresponds to the minus eigenstate is in fact antipodal with the plus Bloch vector, and in a sense, and in fact the minus eigenstate is anti-parallel with the magnetic field vector. So this gives you a very nice geometrical picture of what spin up and spin down represent. So when we have a system that has a magnetic field, and we put a spin half particle inside, we'll get 2 quantum eigenstates. We'll get 2 eigenstates. The spin up eigenstate, which is the green one over here, and the spin up eigenstate aligns with the magnetic field when it's expressed on the Bloch sphere. And we also get the spin down eigenstate, which is anti-parallel. It aligns in the opposite direction as the magnetic field vector. So remember that this nice geometrical picture only comes out when we have expressed the spin up and spin down eigenstates as points on the Bloch sphere. If we simply left it as the form of the 2-component complex vector over here, there's no way we can see that the spin up and spin down eigenstates in a sense align with the magnetic field. It is from the Bloch vector, it is from the Bloch vectors of the spin up and spin down eigenstates that we can see that the Bloch vectors align with the magnetic field. So this is the whole reason why I wanted to go through the representation of spin up and spin down eigenstates as points on the Bloch sphere, because they give you this very nice geometrical picture, and this sort of explains everything. It explains why the spin up eigenstate was called spin up, because it's aligned to the magnetic field, and it explains why the spin down eigenstate was called spin down, because it is pointing down from in the direction of the magnetic field. So yeah, I hope that this correspondence is extremely clear to you right now. So I think that is roughly the end of the video, but I would like to once again go through everything we have gone through as a summary. So where do we start? We started over here where we said So this summary page is very useful right now. So let's see what color I can use. Let's use pink. Let's use red to go through our entire diagram. So we have first started off from the quantum system. From the Hamiltonian describing our quantum system. Then we wanted to find the eigenstates of this system, the eigen vectors of the Hamiltonian. So the eigen vectors of the Hamiltonian, there were two of them. One is the spin up and one is the spin down. And if we express the magnetic field in terms of polar coordinates, then we can get the spin up and spin down eigenstates in terms of the angles theta and phi, which we use to define the magnetic field. Then we went through why we call this spin up and spin down is because let's see, I have some space over here. Red is not a very good color. Then we went through why we call this spin up and spin down. It's because when we have the spin operator in the n hat direction operating on the plus eigenstate, then we have the corresponding eigenvalue plus h bar over 2. And when we apply the spin operator on the minus eigenstate, then we have the eigenvalue of minus h bar over 2. And that justifies why we called it spin up and spin down eigenstates, because when we apply the spin operator on it, we get essentially plus half and minus half as the spins. And then we expressed these eigenstates as points on the Bloch sphere, and we found out that it has a very nice geometrical picture, as you can see over here. It's a very nice geometrical picture where if we take the Bloch vectors of the spin up and spin down eigenstates, we can find that the Bloch vectors corresponding to the plus eigenstate is aligned with the magnetic field vector. It's pointing in the same direction as the magnetic field vector. And if we take the Bloch vector for the minus eigenstate, we can see that it is aligned in the opposite direction. It's pointing in the opposite direction as the magnetic field vector. So this gives us a very nice geometrical picture of what the spin up and spin down states represent. Yeah, instead and this picture would not have been possible if we simply left it in this two-component vector form. So with that, I think I've come to an end to the video. I hope that you have enjoyed this lecture, and yeah, if you have any questions, feel free to email me. This is actually the first video in a series that I intend to make on Berry phase. Perhaps I'll just do one more video on Berry phase, but originally I wanted to cover the idea of Berry phase for spin half particles in one huge lecture, but I realized that I need to first make a video on spin half eigenstates in the magnetic field. So in the future video, we will explore what happens when this magnetic field changes in time. When this magnetic field changes in time, you can get that the spin up and spin out eigenstates that accumulate something known as the Berry phase if the magnetic field goes through a cyclic evolution. So yeah, I've come to the end of the video. Please leave a like if you enjoyed the video or found it useful, and leave a comment if you have any feedback. So yeah, thank you very much. Have a nice day.